all for tuning in the ML workshop channel for this talk on high-level error message for module through diffing. This is a joint work between Gabriel Radan and me, Florian Angeletti. Error message for module are known to be quite lengthy and sometimes even hard to read for ML languages. Typically, if I try to generate a string map module using the map.make functor of the OCaml standard libraries, and I make a small mistake, I'm repeating the string argument, then I get this kind of lengthy error message, which tell me that the map.make string module is not a functor, and it is indeed it is not. But it is not really the root cause of my error. And through this talk, we are proposing a method to get error message that gets straight to the point, that tell you directly that you added a string argument that wasn't needed. So, but first, why do we get this lengthy error message in ML languages? The core reason is that there is quite a discrepancy between the theoretical side and the practical side. In theory, the module language is the most complex part of the language. In real code, most people have maybe a shallow hierarchy of the module, a handful of functors with fewer arguments, and that's it. Nothing really complicated. Which means that a typical example of functor would be, for instance, a graph functor that takes a vertex implementation and an edge implementation and implement a graph module from these two arguments. And if we have this kind of simple functor, which kind of error can you do when using? Well, one possible error is that I give the functor an argument that is not necessary. For instance, I can give it a label implementation because at some point in time the graph functor needed to have a separated implementation from label. Or maybe I was distracted and I forget to add the vertex module in the application and I applying the functor to edge directly. Another possibility is that I could be using the wrong module, using the label module in place of the vertex module, for instance. All these errors are frequent during refactoring because the type of functor are very much in flux and it can be easy to add, remove, or change an argument. Unfortunately, classical error message only considers the last alternative, and if I'm using an extra label argument, the error message that I get is telling me that the module label does not match the vertex signature. Surprise, but yes, I already knew that. I already knew that label were not the vertices. What I wanted to know is that this label module argument was not necessary at all. So in order to get better error message, we need some more perspective. We need to keep the context of the multiple application and consider the argument as a list that we can match with the list of parameters defined in the functor definition. And once we have two lists, we can use diffing algorithm to try to match them using addition, deletion, or change. Typically, using diffing, the errors that we get looks like that. So if I apply the graph functor to the label, vertex, and edge module, I have an error message that tells me, first, my functor application is tight. I have three arguments, label, vertex, edge, and this three argument doesn't match the vertex and edge argument because the label argument is an extra argument that is not needed. Similarly, if I forget the vertex module, but the next module, that I give the edge module, I want to be told that I'm missing a vertex module and that my argument seems like the right second argument. And it is only when there is no no other option that I want to know that my label argument was used instead of a vertex parameter. Label and the label signature doesn't match the vertex signature. And it is also nice to know that my second module argument fit in the functor. So how does this work? How do we get this kind of nice error messages? So the error class that we have seen this far are addition, deletion, and change. Those are classical errors in string diffing. And string diffing is everywhere, from spell checking to fuzzy search or even DNA sequence matching, which means that it is a well-studied topic. Typical operations in string diffing are addition, deletion, change, and swap. And the first three ones match or problematic. And since it is a well-studied topic, there have been many distances that have been studied and many algorithms are available. In our case, with addition, deletion, and change, we are interested in the 11th stage distance. And in our specific implementation, we choose the Wagner-Fisher algorithm. So the Wagner-Fisher algorithm in one sketch is a classical dynamical algorithm. We try to match two strings by computing a matrix of the optimal distance between those strings. So here the algorithm is computing that the distance between BCD and ABXDE is 3 because I can skip the R argument, take the B argument, change the X argument, take the D argument, and skip the E argument for a distance of 3. So more precisely, we are using a dynamically sized variant of the Wagner-Fisher algorithm for computing distance with addition, deletion, and change. We are using the OCaml type checker as a black box for doing a module comparison, and then from there we are doing a number of comparisons that is at most quadratic in the number of syntactic argument or parameter. And all of this is already implemented as a patch on the OCaml compiler, available at the following URL. And once you have done that, we can identify very complicated error, unreasonably complicated error. For instance, here let's have a look at this. Let's cherry pick. For instance, let's cherry pick 16 arguments from the OCaml standard library module, standard library. For instance, let's cherry pick 16 arguments from the OCaml standard library module. Then we can define a little functor with 8 arguments. Personally, I never use functor with 8 arguments, but let's say it's a little functor. And let's try to make some error when using this functor. So here we are applying this functor to 9 arguments. There is already something wrong, and we get this error message that tells us first the first module A match. Well, this is good. The second A argument is not needed. The B argument match. The C prime argument is not a C, so it doesn't match. We are missing a D argument. The E argument is the right one. F prime is not F. G and H match, and the last argument is not needed at all. So we have a very complicated functor. We apply to far too many modules, and we get a very simple to understand error message. But then we can wonder if it still works with dependent functor. So because for dependent functor we need to be careful because the type of the parameter of the functor argument depend on each other. And yes, this worked quite well. For instance, if I define this dependent functor when the type of y and z depend on the type of b, and make a small mistake, I get a reliable error message. In fact, it's easier to look at the error message to identify what error I make in the functor definition. Because yes, the error that I make was simply I forgot to define the module Y, and this means that I have a module error message which is simpler to read than the original code, which is quite something in fact for dependent functor. Another strange thing that you may have noticed is that I have a dynamically sized variant of Wagner-Fischer. Where does that come from? Well, functors are complicated. And in fact, in OCaml, they can even be variadic. It is possible in OCaml to define a functor that can be repeatedly applied to the same argument as many times as you want. And in order to handle this case, our Wagner-Fischer algorithm resizes the matrix of distance on the fly. But the algorithm is still guaranteed to terminate, which means that we handle even this very complicated case in little known corner of the languages. What about swaps? Swaps are a quite common operation in string diffing. But for our case, we weren't sure how to mesh well this error in the textual output. We may consider at some point to handle the subcase where all arguments are here and you only need a permutation between all modules to get back a rightly typed functor. For instance, if I apply graph to edge and vertex, I could have an error message that tells me, did you mean graph vertex edge? That could work, but it needs some works. So then the natural question is, does this scale? Because as I said earlier, I have a quadratic number of module comparison, and module type checking is a quite costly operation. Can I really do a quadratic number of them? Fortunately, at the end of my error message, there is a human. And humans are quite a slow creature. They can wait a whole 50 milliseconds for their error message and don't notice anything. And another important point is that I'm computing my error only once. Because after I've computed my error message, I'm stopping. I'm stopping, which means that I can take my time, and my only deadline is the slow human at the end on the other side of the screen. So we have two competing effects. Which one matters at the end? So let's try to go big. Let's try to define a not that small functor with 26 arguments. 26 arguments just because 26 arguments, one for each letter. We pick those modules from the standard library module of OCaml, so they are quite big modules. And then we apply this module to making a few mistakes along the way. You can see that we have a quite lengthy argument comparison, and we get the whole error message in 100 milliseconds. 100 milliseconds for a functor with 26 arguments is totally okay. But maybe we can go even wilder. The advantages of variadic functor is that I don't have to the advantages of variadic functor is that I don't have to invent crazy definition of the functor. I can just give it a crazy list of arguments. So here we have 223 arguments given to the variadic functor, and we get the result in 300 milliseconds for hundreds of arguments. Let's make a short announcement. If at the day of this talk there is anyone in the audience that has existing code with functor with more than 10 arguments, or variadic functor, if somehow you are using variadic functor, then please tell us. Please tell us. Please come out. Please give us an example, because it's very hard to find this. We couldn't find any example of functor with 10 arguments in non-generated code. And we will be very happy to find one, and we will give you a drink, because all these case areas are completely crazy and artificial, and no one use them. No one use them except for tests. So our performance is totally fine. So what can you take away from this talk? We have applied diffing for functor application and inclusion to get nice error message that identify common mistake rather than try to describe every module type inside. And this works using a non-optimized version of the Wagner-Fisher algorithm. Why it is a non-optimized version? Because optimization didn't matter at this point. This gives, I would say, very, very nice error message as far as I'm concerned. So there's still more work to do. In particular, we are very interested in applying the same technique to signature difference. In fact, the groundwork is already present in the patch for functors, which already built full error tree, but we still need to write the user interface, because it's the human at the end that matters, and so user interface are really important. And once we have that, we can move to other structural types. In OCaml, this means object and polymorphic variant. Then, when everything is here, we can try to tie all this level of error, all this level of diffing together to use the fact that we have no better definition of what is the size of the difference between module to get even better information during diffing. And we could even get fancy and try to use 3 diffing algorithm and suggest user to move or rename its submodule. Maybe, or maybe not. Anyway, thank you all for your attention.